I can just give you a few minutes to read what I said. I just give you to understand the question. Any question? So I want you guys to read this question so you understand what I'm saying. So we'll do some examples. You will understand it better. Are you reading it, Gogo? Are you reading it? Gogo?
Yes, I'm reading it, sir.
Kisley, are you reading it? Kisley, are you reading it?
Yes, sir. Yes, sir. Yes, I'm reading it, sir.
Frank, are you reading it? Frank is not talking. Understand it? Oh, I can see Gogo. I can see Gogo is copying the exam. That's fine. Gogo is making some notes.
Yes.
I can see you. Kisley is not making notes. I'm seeing him. He's just looking. Kisley.
No, it's already nothing done, sir. I'm nothing done, sir.
You're nothing down, but
see my pen. Look at my pen. Look at my pen.
It's only Gogo. I can see his head moving up and down, so he's writing. Writing. Frank hand his head. So when you finish, let me know. Okay?
Okay, sir.
When you just let me know so I can continue.
All right, sir.
I had his face. Daniel, I hide your face. Bring your face fully. Don't hide your face. He's doing his half of his face. Bring it. So can we continue now?
Yes, sir. Go ahead.
I should go ahead
continue,
now.
Sir.
Okay, I should continue. So now, how our impedance relay is set. Now, remember, the impedance. So our measure where we are setting now is the impedance we are setting. That's what they call it, impedance. You understand? So that's what they call it, impedance relay. So it's our impedance we are setting. So in this case, now they have given us the generator data. And they say our generator data is 141.5 MVA and 10.5 kilovolts. That is the line voltage. I think I said yesterday now. That was logging now. Okay. Go.
Yes, I'm hearing
you.
Sir?
Yes. Okay, see, send the password and the distance to Eze. I don't know if you, I sent it to him. He said, send him.
I just send it now.
That's fine.
Yes, I've already sent it to the platform.
So I don't know why he complained.
I think the problem is that the zero, the last zero, they are putting it as O, so they should use zero as the last digit word. That's a mistake.
Figure.
It's not O, it's zero.
It's figure, yeah.
That's it. Yeah, it's figure.
It's figure.
Yes, it's a figure.
It's already in our
WhatsApp
group.
Right.
Let this go to the WhatsApp group and he will see it.
I just posted it already.
Let me call him now. I don't know why
it's already there. It's already there.
Okay, it is there now. Okay, Gray was out.
Okay, let's go ahead, sir.
It says the app now. Easy, go to staff confusion. Easy, change, let's go, it's not O.
Engineer Eze.
You put that zero, that's why. Easy. Huh?
Engineer Eze.
So this solution now.
So,
okay, now I'm back. Okay, that's fine. So now we must calculate the load, the impedance load on the primary side. For us not to calculate for the secondary side, because it's the secondary side that we are going to use to set up our impedance relay. As I told you, our impedance relay is here. Our impedance relay is at this point. That's where we're going to set it. Inside here. Okay. So in that case, that was what I was saying now. So now, this is what the primary side load. And load, what is the impedance? What can become impedance for us? Huh? People are quiet now. Go. Define impedance for us here. So you know the formula. What is the formula for impedance? These people there. Voltage is equal to what? Impedance times current. So now, if you make impedance the first formula now, what is it going to be now? Voltage. What? It's going to be what? If you get both sides by impedance, what are you going to get?
Sorry, sir. Where are you?
What I mean? Don't just the question. You see what I mean? It's not even to talk. Now, I want us to establish, I want us to come out, you want to contribute how we get this. Not after now, you asking me, it's simple. Here, we want to do this here, look at see what I'm saying. Are you seeing it now? Now, from this data, I want us to arrive here. Now, they are giving us what the voltage. And they are giving us the current. So, our formula to find the load impedance of the primary side is what? This voltage times the percentage or the operating percentage of the impedance. This is the operating. That is operating at 95%. So you must times it with what? With your voltage. Then divide by your current, which is this. And that gives you that. So this is now the impedance on the primary side. And it is assumed that it operates at 1.4 times the rated current. So now, this operating at 1.5 times the rated current. This is our rated current. And our operating time is this. So the primary side impedance is approximately equal to 0.4. You are quite quiet. Okay. Now, the secondary side impedance, you must not include the CT and the PT ratio in this case. And in the secondary side, we have our voltage. This. Look at this voltage here. This kilovolt. Of the PT, look at it. Look at it here. That is it. This 10 raised to power 3 is that. Because they say this is 10.5 kilovolt. So that is a kilovolt. And now when you not get that, when you not calculate this, and times the CT, which is this is CT, then times the impedance of the secondary that we calculated, then that will give you 9.283 ohms. Telling you that our impedance must be set within this range. Within this range. That's how we're going to set our impedance. And since we have 9.2, we can just take the whole number, not a decimal. So our impedance here relay should be set at 9 ohms. Okay. Grace, you understand that?
Yes, sir.
Okay. So that is how we set our impedance relay. since our time delay is between 1 to 0.5 to 1.4. So our time delay, you can set it as 0.5 to 1. That will be our time delay. Because they say it's 1.4 times rated current. So if you set our time delay within that range between 0 to 1.4, so we can say if we take 0.5 to 1, then as our time delay is second, then we're going to work well. So that is the range. It's not simple, it's technical, but it's not more technical. So like now, so these are the two things, the dictionary relay and the impedance relay you can use to protect your generator. Apart from the abnormal condition like frequency and out of step around the road, but these are the major protection schemes you are going to see in your generator. Any question? So I want to remove this so that we can go into another slide. So I want to, push it to drag it people into asymmetrical component a bit. We'll soon finish. So that I want to finish by 12. As I said. So any question? Are you
Sir, I have a question. Okay. I have a question.
Please go ahead.
Yeah, from the question, they says our impedance is approximately equal to 0.49. From the question.
Approximately.
Yes, equal to 0.49. Yeah. And our impedance at the secondary part, is just, can you just explain that?
Okay, I know what you're talking. I know what you're talking. Now, as I told you, we're going to use the secondary side to set our impedance relay, not the primary side. What you talk that 0.4 is our primary side. Do you hear me now?
Okay, I hear you, sir.
So that one is the primary side. But the one you are going to use to set your impedance relay is the secondary side. Okay. So that's what we have 9.2.
Okay.
Yeah. So we don't use that. We don't use that. It's the secondary side that is really going into the operation with other side of the distance. The primary side is coming from the generator, but secondary is going to let out.
Okay.
So it's the letting outside we're going to use.
Okay.
Because if you use the primary side, and you know that the load will be increasing at the secondary side.
Yeah.
Is that okay? So it's very important. It's a good question to ask like that, so that you know. So it's the secondary side impedance that we say, because it's the secondary side impedance. You see that the CT and PT appear.
Yes.
In the primary side, the CT and the PT did not appear.
Okay.
That is it. So that is why we use the secondary side. Grace, are you following?
Yes, sir, yeah.
So, any more questions? I'm making it more practical for you guys, so that even if in factory or in the consultancy, you cannot do one of these things. You understand? You cannot do one of these. Even though you go to US, anywhere in the world. That is it. I'm giving people, if you go to US, go to UK, Germany, Japan, China, they can't give one of these. Is that okay?
This one is universal standard.
Yeah. The universal one. And what I'm giving you guys for this course, I'm giving, even though you travel out, go to anywhere, but Professor Emeritus, let them call. Yeah, so that is the report I got this morning.
That is not true. That report is not true.
That Professor Prof, you do teach that he didn't big hand that I come now, give it for handout. If you like,
that is not true.
if you like, it's up to you. But
please ignore that rumor. Is there
just to digress a bit, I want to push you to link you people the symmetrical component to this for protection at their link. Now we have finished all this one, the positive sequence, negative, it's, I won't talk about it again, isn't it? It's not, we'll talk about positive sequence, negative, and zero, it. You know this diagram, isn't it? Then this operation, that this operation is part of the assignment I gave you. You're going to use this where, and that's what I bring it. It's not, it's in your node, it's in the material. All this formula here, you're going to use it. So it's just for you to manipulate it. So we define the alpha last time. So that is why I bring it. So you should not be panicking. All this formula you're going to use in the assignment that I want you to use it. And so all this. So I think why you guys should complain that you don't know it. It's what we discussed. So then this assignment is there as well. So yeah, so this is what I want to go now in the generator. So now we can use we are told that symmetrical components make all, or in sequence domain, that our voltage, that going to follow the space voltage, that it must incorporate what the positive sequence, negative sequence, and zero sequence, isn't? Like these are phase voltage. Yeah, these are phase voltage for the motor. Look at it. Where's my cursor? These are phase current. These are phase current. These are phase current. These are phase current A, phase current B and C, and these are voltage here and voltage here, voltage here. The voltage across the impedance. Okay, and we are told that in sequence domain, that for us not to get this figure here, that this figure that is equal to what? Who can say to us? What's our figure here? How can we detect our figure here? In this generator now, this phase A current is equal to what? In later, Frank, tell us. I'm seeing you. Look at me. I think Frank. Frank is being quiet. He's running. Is it Tano? Can you keep me now?
Phase A current is equal to VAZA, ZF.
Sequence domain, not the phase domain. In sequence domain, we are not, look at the topic that's symmetrical component. In sequence domain, go, can you help us out?
It's equal to IA is equal to IO plus I1 plus I2.
IO plus I1
plus I2.
Plus I2.
Yes.
Is the nomenclature correct? Gogo,
No.
the nomenclature is correct?
No.
Say it, put it in the right way. Fast now.
And it's going to be the total IT minus the total current from the generator minus current IT2 plus IT3 equals to IT1.
Well, no, our nomenclature, if you don't have to, that's what I want to say this now. Our nomenclature in sequence domain, we say is what? I positive, I negative, I zero.
Yes, sir. Addition of the current. I just forgot that. I'm right now.
Okay.
I'm 70% right, sir.
70% right. That's why I'm bringing this now. It's like okay. So that's how you must get. That's how you get this current here in the sequence domain of the generator. So you should not know it right in sequence. Not in phase domain is one value, but in sequence domain it is incorporate the phase positive, negative, and zero sequence. So also the voltage, the phase voltage is here. Is going to be what? The voltage plus, voltage minus, and voltage zero. That's what you call the phase voltage. Very well in sequence domain. You have to understand the sequence domain and phase domain. I have started this over and over, over and over, over and over. Grace, do you understand that?
Yes, sir.
Do you understand that?
Yes, sir, I do.
Well, you should know when we are working in sequence domain and in phase domain. Like to the asthma I gave you people, it's in phase domain. So I must see the three sequence diagram in each of the assignment. So you should know that's what bring this because you are shouting that you go to Cambridge to do it. So in that yeah, keep quiet now. In that in the transformer, so we have the three sequence. This is the sequence we have, the sequence diagram we have. So this is the sequence diagram. So you must work on the sequence diagram. So each of the assignments, you must give me the sequence diagram. You understand that? So that's there. So then we have got this. So you know the operation. So and now you must connect again the components together like this. You must. I'm giving you the tutorial of the assignment. Yeah. So you, at the end, you must connect your sequence diagram. I'll see this way. Now, discuss about the current behavior of a synchronous generator. In synchronous generator, we have a set of values. We have three sets of currents. And we have the positive, the zero, the positive, and the negative. And I told people in this class that in the positive sequence, that the magnitudes are equal. That the magnitudes are equal. Okay. Let me bring one diagram. Understand this diagram. This is first current behavior of a synchronous generator. Now, the two first cycle of this response, it is what 0 to 2 cycles of this response. That it is we have a sub-transient period. It's a sub-transient period. Then after 2 cycles to 30 cycles, we have full transient period. It's transiting from one state to the other. It's a transient, that is a movement. That's what we call it transient. It's a movement. It's transiting from one state to the other. So, and now then from 30 above, we have what a steady state period. Then the response is trying to gain stability. It's trying not to stabilize in steady state. That's going into 0. Is that okay? So now it can see the magnitude. This is what a positive sequence. The magnitude are equal. You can see from outside. You can see from here to here. It's equal from here to here. So the magnitudes are equal in positive domain. That's in positive domain, in positive sequence. But in negative sequence, this magnitude here and magnitude are not equal. They are not of each. They are not of. They don't share each half circle. Sometimes you can bring 1/4 to 1/4 circle. That's it. I want to explain here. So now I'm going back to here to go to here. So you can see here. Here we have what the 0 sequence, and you can see the magnitude are not equal. You can see. So when you are running simulation. That's why you check whether your simulation is not is the magnitude, the magnitude high, if they are equal. And you can see that in a negative sequence, the magnitude are not equal. You can see that the positive side of this response is higher than the negative side. You can see from here to here is higher than from here to here. You see, and our positive sequence, you can see that we have equal. We have equal. Then our negative is also null. So that's why you check whether your response is correct in your simulation. And then we are calling it when you're doing validation. Is that okay? Fine. So it's very important. I want to bring this down. So now, this is just a simple fault current. Simple generator behavior. It's a generator, it's just a simple. And this generator is what? It's a sinusoidal one. Look at it. It's a sinusoidal one. And it's in time domain. Of course, it's not in frequency domain. And now we have, and it's also a transient AC model. So, which means there's going to be some transformation in the line. And now, this, our generator here, can be equal to the what? Can be equal to what? The impedance, equals what the impedance. This impedance here. And that is this impedance here. And now the inductance is taking what? Is the integral. We take integration of that, of the inductance. And we take that. This is our resistance. That is it. So now, if you are trying to now to work for this current, the current flow, this current now, this current, if you are going to take the loop. So if you take the loop of this, then you're going to have the Vn over there sine that. Everything here. Then you're going to now incorporate also that. So if you take what the integral of this, you're going to have that. So if you do the looping, you are going to have this formation here. And then you cannot obtain this current. That's how you get this current. We are talking of this current. So this is how you can obtain this diagram. That we are talking there. Is that okay? So if you now plug if you now input the voltage, the impedance, omega already, omega is constant, 2 pi arrow. 2 pi is 2 pi. 2 pi. You can take our 50 hertz, you can take F as 50 hertz, you can take pi also, 22 or 7, those are constant. Then you're going to have the phase angle, and this is the phase angle. This is the angle of the line. So if you now get that, you cannot input this, and you're going to have this response. So you can do that on your side. You're going to get that. And again, they have defined what the impedance for you. Look at their impedance here, and look at their alpha here. It's obtained already. The omega A over R. That's why you can get your alpha and your Z. So all this one can be given. Or alpha already. You can use 120. You can use 240, depending on the detection of your angles. So if you want to now maybe if you want to work now on the domain in sequence, the first one you can use 0. You can take your alpha to 0. Then the second one you can take your alpha to 120. Then the one you can take 240 or 140 or 240. That the case will be. So it depends on your judgment. But the power here is given by this. So this is your rotation, angle rotation. We have discussed that. If you check anyhow, maybe you can see minus 120 plus 120, 0, and all the rest. So that we cannot obtain the stress sequence, the negative, the positive, and zeros. So I think I'm going to give people assignment on this. It's like you're not to run for simulation, and you will go to cry more again. You will not cry. I'm helping you guys. I'm not trying to weaken you guys, but if you know it, that is good for you. So now, if you input those all these things here, you are going to get this response very, very well. So should I give you an assignment now after this? When you finish this, maybe after this, if I give you people. Would you like it? I want you to run simulation. We use MATLAB. You talk now.
Let's finish the first assignment. So that we can come to this one. Yeah.
Yeah, because I want to go to raw simulation.
That's the problem. We'll do that.
So you should try to lay a MATLAB a bit now. So that you guys, so in your project, you can work something. So that is it. So now it's not to now I want to teach you how to accept the DC in the signal generator. We can offset it because the DC's component incorporate what we call harmonious problems, or in terms of harmonious problem in the network or in the motor. So now we want to get rid of that. What are we going to do? Now, if we want to get rid of that, now to offset the DC component in the generator, we are going to put our this where we have this sign into alpha plus 5, we put plus or minus 1, or alpha is equal to what? 5 plus or minus 1, 5 all over 2. Then if you not input this formula into that equation, then we have not offset the DC component to maximum. So if we want to eliminate it completely from the component of an generator to avoid disturbance, the DC component disturbance, then we're going to put this thing, we're going to put that equal to 0. So if we remove this from that formula, then we have completely removed what? The harmonious component or the DC component in the generator. This is a technical formula that I'm giving you guys. So you can know it well. And now if you also put alpha into 5 in that equation, then we're going to have no DC component already. Or if we now put alpha equals to 5 plus 5, then we have removed the DC component from the generator. And that reduces what? The disturbance, the harmonic disturbance in the DC component in the generator. So this is a way that we can offset a harmonious component in the generator, because harmonious component that come from DC, introduce what? Disturbance in the generator that slow down the smooth running of the generator. So that is a technical point. It's not, you can't get it much from any person. Put it very well. And let this point be in the tip of your head. Alright. So we have done that. Then try to copy this. You didn't have to copy here. This button. That's why I say come with loads. This thing. We can't just stop it. You see, when you're lecturing, let me tell you, when you're lecturing, is there idea will be coming in. I just put this in this morning. When I was trying to review that. I told you, it's good, because I don't think I don't bring it. If I don't bring it, guys, I cannot give you in the generator. We have a low impedance grinding and a high impedance grinding. So, although more of the low grinding, impedance grinding that always appear now in the factory or in the postal network. Although, but the high impedance grinding also appear, but it's expensive. But people always use the low impedance grinding. You understand? That they come up and money or not the rest. So all along we'll be doing the low impedance grinding, and we can also do the high impedance grinding. So I don't want to know that there is two grinding. We can grind our generator in two ways. We can grind it only by using the resistor to ground, or we can employ a small transformer here with a resistor to ground. And we call it what? High impedance grinding, because this one is not part the impedance of the generator of the transformer here with the normal resistor, this resistor. We are not connecting this. So if we're not connecting what? This transformer here, this transformer we are connecting it to this resistor here to make it more higher. And that's why now we will call it for high impedance grinding. So whichever way you can grind it, fine. So I want to tell you guys, because if you go to companies and they have this, you can also, if you want to upgrade it so that the electric can be more stronger, then you can go to high impedance grinding if you have it. Okay. So, but that's for technical, that's for high consultancy job. Okay, that's fine. I'll say it. No impedance grinding, single phase to ground fault, and that's where you can apply it. So you can only apply the single to grind, that is low impedance grinding of generator that have up to 320 amps, 320 amps, that the current should be 20 amps. Then
20 or 200 amps.
200 amps, 200 amps. Then for high impedance grinding, it's between 5 and 20 amps. Okay. So that's this is left to you. So it's just for your information. It's very good. So we're closing now. So our topic today, our protector, our generator stator phase port. I have told you that this is just a different relay that it phase port, and now our protector skin is 57G. So if I have 57G, it's knowing that we put that you come on that leave that now. You're a fucking guy. So if you now have that, if you not see this 57G, it means that we are you this special day. So I'm trying to highlight only this number you're going to use. Sometimes they will not give you this diagram, they will only mention this figure. Then if you know is what this diagram you are trying to, this problem you are trying to. Then where you can apply 57G used to protect 3 phase to line, 1 phase to line to line, multiple phase. So that's why you can apply this 7G protection. This protection is line to line, phase to phase, 1 phase, 3 phase, 2 phase. So when you see this figure, you should know that they are telling you that you are on 3 phase line to line, 1 phase line to line, or multiple phase. You understand that? So that's what I'm trying to highlight here. And also, this is our face-to-face call. Is 87 stage. We're going to apply that differential relay. We are working on this, so I don't want to talk about it. So and now this is a 3-phase call. In 3-phase call, now 3 phase has a call. Yeah. Okay, in 3 phase, you can use 87N, 57N, 59N, so they can do this figure. But you should know this is what the protection they are telling you to do. And remember, in your sequence domain, the current, look at it, must be 1, 2, 3, must be together times ET. Very, very important. So also, just like that. Now the current here, the neutral current is the first current times CT, and the neutral again is that and there. So you can calculate that. Those one is not too difficult again. We have done this in the previous example, but my emphasis is how to use this number, how to identify them. Because you can go to factory, and what they're going to see is only this figure. Only this figure. Only this number you're going to see. You cannot see any name. So you should know that what they're talking about is the differential relay they're talking. So don't be confused with that.
Sir, you said what are they talking about?
I'll explain you. Shut up there. I just explain here. I said what I'm talking about.
No, the last I did not get the last statement you just made.
Go explain to you. I can't go because our time. So also in first domain in our single phase call it's easy. In single phase call, it's the thing that you are current must be 3. That's what I'm telling you. The positive, the negative, and the zero. In first domain, we have done the same in our 4. not please here to include in your anything you're going to do is to start safe with the CP. So that's what we're doing. So I don't want you to, I'm going to go to do assignment. I think we're not doing before. That's why I'm going to here. So then reverse your form. Is that okay? Time, you're going to check your one, yeah. Okay. Grace, is okay. Grace is
sleeping already.
Come to the protection, science it by the city current. Then the current in the protection domain, in the protection here. Is that okay? So I'm not going to get document again first for the beginning again here.
Yes, excuse me. Doc, sorry. Yes, Doc, I want to plead. Sorry for taking you back. It's just the coronavirus. Yes.
But wait. People are used to take period. You are here complaining.
So, at the first domain, most of us we are not in class when you teach that topic. What? Hello, I'm asking questions, sir. Like I
go ahead.
Okay.
If you have the material, it's the material.
Go. Okay, sir. Okay, bro. Okay, I'll go for the material.
Conversion from first domain to second domain and second domain to first domain.
Okay.
You are not reading. You're not reading. That's having problems.
Okay.
And that is why I don't want to go to again to explain it again. We have to save energy. So, can you put it today now? It's 3 o'clock now, so I want to leave now.
Thank you, sir.
I have it with